You hear me now? Okay, I'm gonna switch to our big faces real quick. Okay. All right, I think we are good to go. I'm back here in the background if everybody is able to see. We have with us tonight Kyle Dawson. He's a professor at the University of Utah in the Physics and Astronomy department. I think you came on in like 2009. Was that your first year?
That's exactly right.
Cool. So yeah, he's been there for quite a while. He works with the Sloan Digital Sky Survey. Uh, Particularly, do you kind of do like the whole thing with everybody, or you focus more on just boss?
Just BOSS and eBOSS, the cosmology components.
Gotcha. Okay. And
It's hard. You can't do it all. There's too much.
yeah. So he's been working with that for a large portion of his career, and so he was involved with the latest release of data that a lot of sites are saying it's like the record-breaking 3D map of the universe. So some people might have seen that recently, which is also the reason why we're here talking with him tonight, just so he can give us some insight into what's been going on and how his work goes on with it. What does it actually mean? Some things like that. We're open to questions, so if anybody has any questions during his talk, feel free to post them onto the comments section, and then we'll pick those up and he'll answer them as soon as it's relevant to do them. So let's welcome Kyle Dawson. Yay, hello. So if you're ready to go, you can maybe do a intro of yourself if you would like, or you can just get started. It's up to you.
Yeah, well, I think Paul did most of it. I'm the PI of the project, the cosmology project that I'm going to present today. And as Paul mentioned, it took us 10 years to collect all the data, publish many, many results and intermediate results. And we just got all of our final measurements and our final cosmology interpretation out on July 20th. But it's a 10-year endeavor, and it was total relief to have that out. It was a wonderful feeling. So I'm going to talk about what that was, what our results are, how we ran the experiment, and I'm going to just kind of hit snapshots. This is only meant to be 20 minutes and an introduction. So please interrupt or save your questions for later. The whole purpose is just to be able to have a forum for people to ask anything they want about cosmology. I am going to be a little more technical than a lot of coverage. I'm not just going to talk about a map. I'm going to talk about the physics that's embedded in that map and how we pull out that physics and what we've learned about the origins of the universe. Okay, so as I do so, I'll have about 20 slides. About a third of them are just going to be some background on cosmology. Something like a third of them are going to be about how we ran the program. And then like a third of them are going to be about the results. So here's our outline. Okay. So this is a very classic image of the history of the universe. There's an amazing amount of information embedded in this, right down from the timeline, which passes from left to right. On the far left, you see the beginning of the universe, the Big Bang. Then you see a period all in white called inflation. The way I look at the universe is I look at these two events as just setting the stage for the rest of cosmic evolution. And in physics speak, I would say they set the initial conditions. We don't know a lot of the physics beyond what's in this time period. It's about the first 10 to minus 32 seconds after the Big Bang that I'm talking about here. So that's roughly a billionth of a billionth of a billionth of a millionth of a second. That part of the universe we don't really understand very well. What comes out of it that's the most important thing is that if you look along the shape of this tuba-like object, you can see that from the Big Bang to the end of inflation, that white period, you can see it's very steeply getting wider and fatter. That actually is representing the expansion of the universe and how quickly it's happening. So what happens in that inflationary period is the universe expands by many, many, many orders of magnitude. Like we say, like 60 e-foldings. That's something like 20 orders of magnitude in size. It happened almost instantaneously, and it basically, like as I said, set the initial conditions for the rest of cosmic evolution. And that's what I study. Is I basically study from those initial conditions, what are the physics that take place for the next 13.7 billion years? So as I look at this figure, after inflation, you can see this colorful background, this white and or green and blue and red. That is what we call the cosmic microwave background. That originated about 300,000 years after the Big Bang. It is an image we can observe in great detail. It's some of the best cosmology and some of the best understanding we have of the universe is through images of that. But it's only one epoch of time. It's basically like an instantaneous snapshot of the universe as it was 300,000 years after the Big Bang. There's no galaxies, there's no quasars, no stars. At that period of time, there's just a lot of electrons and protons that are combining into hydrogen. And in some areas, there's more, and in some areas, there's less. And the statistics of where there's more and when there's less carries a ton of information about how much matter there is in the universe, what type of matter there is, dark matter, electrons, protons. There's a ton of information there. And then as you keep progressing from that cosmic microwave background there on the green and the blue towards the right, you see 13.7 billion years of evolution. You can see galaxies and stars starting to form as you go to the right. You also see the universe is still always getting bigger. You can see this grid-like pattern here. That's like, imagine like rolling up graph paper. The graph paper sets the coordinate system for space. So that coordinate system keeps stretching and stretching and stretching as the universe grows. And you can see that these squares get bigger and bigger and bigger as you go to the right. You can see it's happening gradually up until, about the last quarter of this image. Then you start seeing it accelerating again, where it's getting fatter quicker. That is a turnover that happens something like, several billion years ago, where our universe transitions into this phase that we really don't understand very well that causes it to accelerate. Okay, so what I study is the physics that lead to that acceleration. And I also study the physics that allow those clustering, those overdensities, underdensities in the cosmic background to collapse and grow into more massive structures. So all of that is modeled by fundamental physics. Okay, so what are the
Kyle, when you're talking about the collapse of that stuff, would it be a gravitational collapse, or is that something that's still kind of up in the air about how it occurs?
Yeah, so that's a great question. And when I talk about the collapse of stuff, I'm talking about overdense regions that are just a sliver more dense than average over many hundreds of 100 million light years or so, and they range in scale, but you can take 100 million light years as a proxy. And gravity, if you have a bunch of matter, gravity just makes it want to collapse. And it's this game between gravity wanting it to collapse into more dense structure versus the universe expanding and trying to prevent that collapse. So there's this balancing act for all of cosmic time of expansion versus gravity. And then gravity is coupled to expansion, and we try to understand all those physics. And it all depends on what the universe is made out of. And it also depends on what's the law of gravity, which is something that we are also trying to test. Okay, so that's the general model. Now we have a lot of simulations that show how those overdensities collapse over time and start forming bigger and bigger structures. But embedded in there, there's two fundamental things I just said in the last slide. First, here in bold, the universe is expanding with time. And if particles want to get further and further apart due to expansion, it means that's resisting their gravitational collapse. That's going to slow down their gravitational collapse. On the other side, there's gravity, as Paul just asked. It wants matter to fall into itself, and form. When I say structure, I typically mean much larger structure. That's not something you can see like a star or a galaxy. It's just like a kind of like a metropolitan area of galaxies. But it does actually collapse into galaxies and galaxy clusters as well. And what determines our model for that is gravity, which is Einstein's general theory of relativity. And that's more than 100 years old, that model. And there's some phenomenal predictions that came out of his theory. And we're still testing it today, okay? I'm not going to show some of our tests of that, but it's important to know that is something we still try to test.
So, could you just kind of like a clarification? So when you're saying when galaxies are coming together, that would be something similar to how Andromeda is slowly coming towards us, and how we're kind of gravitationally attracted to a few of our other neighbors. And over the course of how many millions of years does this kind of take place, where you're kind of doing the kind of a local collapse, maybe?
Yeah, so these collapse, so your example is, Andromeda is actually gravitationally coupled to the Milky Way. And that enters a regime which we really can't model very well from first principles. So we typically work on much larger scales. And even things separated by 20 million light years or 50 million light years, if they're in an overdense region, they still want to collapse in. And they don't have to be galaxies. They could just be gas clouds over many millions of light years. And gravitational collapse still happens. And it happens from the time that, it happened actually in dark matter. It happens right after right after the inflation ends, it starts happening. And then the photons, when they leave the electrons, that starts happening about after the CMB, like 300,000 years after the Big Bang. So all this stuff is going on for all of time, over all scales. And we actually try to measure that fundamentally over all scales. That's one of our key measurements that I'll show a little bit of, just to give the flavor of our data.
Okay, so one more question.
We measure galaxies falling in over tens of millions of light years into these gravitational wells.
So that would be similar to the thing that was released a few years ago, they call it the Laniakea supercluster. Is that something similar to what you're talking about scale-wise, where you have these different regions of space, even though they're separated by really large areas, they still have a common gravitational influence?
Yes, that's actually that's a really nice visual. The people who did that press release did a great job, and did that work did a great job. And it's so large that the objects aren't bound to each other. They're not going to orbit each other like this. They're just going to slowly fall in like this, really slow. And there's all these gradients in the density field. They fall in different ways. And that image from that work shows all the vectors of what galaxies are going where, and how they're falling into one deeper potential and leaving another shallow potential. It's amazing. We do the same thing, but we do it over the entire volume of the universe that we can observe, not just locally. But at the same time, because we have such a huge volume, we can't do it in as much detail as they do. So we go for quantity over quality.
So I do have somebody did post a question, and this is kind of an offshoot of what I think we're kind of going for, but I'll ask it anyway. And he just Tom asks, will we ever discover dark energy? And I think that's kind of an open question, but you can feel free to answer it however you'd like.
That's a fantastic question, and that's actually the direction I was going in on the right-hand side of this slide. Okay, so let me go into that question. So you can see in my last two bullet points here, when we have this model for how is the universe expanding with time, what goes into that model is So the primary thing in gravity, in Einstein's theory of general relativity, is that matter and space couple to each other. It's not just one particle interacting with another particle, it's actually everything interacting with space. And if you look at those interactions over the whole universe, the matter content and the energy content changes the way the universe expands with time. So photons have a different effect from protons and electrons and dark matter, and they all have a different effect from something we call dark energy. Okay, so when I talked on the last slide that, is in the rightmost corner of this figure, the right 25% of it, the universe starts accelerating again. You can see the curvature is getting white fat quickly. That's because of what we call dark energy. And dark energy has a different effect. It couples to space in a different way than matter does, and has a different effect over cosmological scales than what matter has. And the effect, matter wants to cause space to collapse, so it slows down the expansion after inflation, whereas dark energy does the opposite. It makes the universe want to expand faster. And we don't understand that. But we observe it very, very clearly. Okay, and then when we look at the breakdown today, here on the top panel, I can look at how the universe has expanded over some amount of time, and something like 70% of the energy content today is governed by this dark energy. That's why we see this, it dominating the way that the universe is expanding. It's causing the universe to accelerate. That's because mostly our universe today is made out of this dark energy thing. We don't know what it is. And that's one of the primary things we're trying to figure out. What I would say is it really is just a name for the fact that we see the universe accelerating today. That really is all it means. We have ideas of what it is. It actually jives with something that Einstein predicted many, many years ago, but we don't actually know. And that prediction doesn't line up with a lot of other physics. So it's very hard to describe from particle physics why we would have what Einstein has in his theory of general relativity. Okay,
so it would be kind of like different than what we're familiar with like the electromagnetic force and the strong force and stuff. So it's like a completely different idea and a mechanism than those completely.
Yeah, it's not a force. So the electromagnetic force tells you how electrons, anything with a charge interacts with other things with charge or with light. Dark energy is more of a material. And its properties determine how the universe expands with time.
Yeah,
so
I think
it still just falls into the theory of general relativity as a different type of material.
Yeah, I think that was a good point to make, that it's not a force and it's like something completely different. So like when you're thinking about the universe expanding, it's not like something is forcing that expansion.
Something is forcing the acceleration, but not through a different force. It's just its existence interacts with gravity, right? So the force is gravity. So when you have dark energy and you mix it with gravity, you get this acceleration.
Gotcha.
Take matter and you mix it with gravity, you get collapse. So it's kind of opposite, and we don't know why. And if you look at today's universe here, it's mostly dark energy, whatever that is. That's in the blue. And it's about 30% matter. And dark matter, we don't know what that is either. But in cosmology, dark matter, at least in terms of cosmic expansion, dark matter acts just like other matter. So once you get past the cosmic background, they're effectively the same. It's a little, I mean, that's at least in terms of measuring cosmic expansion.
So one more question, kind of related to this. If you're going to answer it in a minute, that's fine too. But Tom also asks, if you don't think we're ever going to discover it, he asks, do we need to rethink gravity so that dark energy doesn't have to exist? So that's like, yeah, feel free to answer that if you'd like.
Okay, awesome question. That's my sub bullet point over here. I say gravity causes collapse in the galaxies, and I say basically maybe we have to rethink Einstein's theory of general relativity to explain it. So there's a couple of ideas out there for this dark energy. One is that it's just its own energy field and it's just something that you would model with general relativity. Another idea is that when you get to very large scales, general relativity is not the correct theory of gravity. And I don't have we do tests of that actually, but I don't have those slides in here. That got to be fairly technical. But we can test. And so far, all the tests show that it looks like it's the best theory, but our tests aren't that precise yet. We can't test things on cosmological scales to the same precision that you can test, dynamics inside our solar system. So it's not that far-fetched to say the theory of gravity fails when you get to really large scales. And the reason it's not that far-fetched is because gravity doesn't work on quantum scales. We've never figured out how to model gravity in quantum mechanics. So it might just be that general relativity is an approximation over a certain range of scales. And then once you go out of that, you start deviating and you start, general relativity deviates from the correct theory of gravity in a way that we don't know. But right now we just can't answer it. That's a big question.
Yeah.
Everything observed so far shows that this dark energy looks like a field from Einstein's theory of GR called the cosmological constant.
So it's kind of like leading back to like Newtonian gravity. That was just like an approximation of relativity. And so this one might just be an approximation of a different version of gravity. So we just need to investigate things a lot more in order to do it. But it's hard given our abilities right now because like the universe, like the time scales of what the universe occurs on this and like the scale of what we're seeing is harder to do than what we would experience in the solar system.
Yeah, it's hard. Okay, so it's hard because in the solar system you can measure things at super high precision because they're right next door. They're close and you can measure them in detail. So like, for example, we have a telescope bouncing radar off of the moon and looking at reflections, not radar, but the lasers off the moon and measuring its distance every day for years and years and years. You can't do that in cosmology. And the other problem is that Einstein's theory is just so good that to find fault in it is just this unbelievable challenge. So
yeah, because that would mean a lot of other things that we have understandings for, like in terms of like black holes and all of this other stuff, would have to be kind of tweaked in order to understand them also.
sure, yeah. I mean, right now all the GR does an excellent job of describing what we see with LIGO, for example, which you told me was a recent talk. So yeah, it's just a great theory, and we keep testing it, and it keeps holding up. People are also doing tests in the lab at really small scales, looking for deviations from GR, and they haven't found anything yet. So anyway, so okay.
Yeah, let's move on to your next point so we can keep things rolling, I guess.
The top panel is basically what's making the cosmic expansion today. It's mostly matter and dark energy, but 300,000 years after the Big Bang, the mixture was different. And you can see that it was mostly driven by dark matter. It was about 2/3 dark matter, but neutrinos and photons played a major role back 300,000 years after the Big Bang. And one other fundamental thing we try to answer is, what are the properties of neutrinos? So that also is stored in our data, although I will just show some results. I won't talk that much about it. But it's just that, we can explore a lot of different things with our data. Not only can we explore dark matter or the matter and dark energy, we can also explore gravity and neutrinos. And we can also do other tests for other new types of particles that I'll talk about. Okay, so what do we do in the end of the day? We use a technique called measurements of large scale structure with spectroscopy. And if you look here, this is our fairly local universe. Every dot here is a galaxy. You can see that we're centered, we're making this map from our perspective. We're not at the center of the universe, but we're centered at the center of this image. because that's how it looks to us. And as you look further out, you're looking at the universe as it was at earlier points in time. And as you go further out, the reason for that is because the light took a lot longer to reach you. So those photons were really old. They're, up to, this, I think in a different unit. I think in redshift, that's what we can measure directly. So I think redshift 0.14 is probably something like 1 billion years ago. I don't, something like that.
So just to clarify, like the redshift, the closer you are, the smaller the number. Is that right?
That's right. The smaller the number. So the redshift is the fraction by which you've stretched the wavelength of light due to cosmic expansion. And if you see if this galaxy, this image, this is kind of getting back to what Paul was asking about with that image, or that result from the Hawaii group. You can see that it's not just a random splattering of points. You can see that they're kind of forming in these filaments and veins. And we have tools and statistics to quantify how things are clustered together. And that is what we use that's what we use to test physics, is that those statistics are predicted by different models. And we don't measure one galaxy or two galaxies and predict anything. We compute the statistics over the whole sample. We usually need hundreds of thousands at least before we can say anything. Okay, and I have this circle with the arrows. There actually is, you can't see it. It's very hard, it's very, very subtle, but there's a feature hidden in this pattern of galaxies that looks like this circle. And when you make measurements as hundreds of thousands, you can pull it out. And that gives you a tool to make distance measurements the same way a surveyor uses triangulation to measure the size of the property. So we just measure angles, and we know the size of the ruler, which is here on the red. And that's actually a key thing we can do to use to measure distance as a function of redshift. And that's our key thing. That's this figure back here is distance versus redshift. Okay. So what we measure it with is typically galaxies or quasars. Basically, what bright objects can we see out there? Here on the left-hand side is a map in look-back time. So how long has the photon been traveling before it hits our telescope? All the yellow are galaxies, the red are quasars, and you can see there's a big gap. And then there's the cosmic microwave background at about 13.7 billion years ago. And then we have other techniques on the right that allow us to observe at higher redshift or a more distant time, but I won't really talk about that.
We do have a couple questions.
Yeah.
One of them goes back a little bit for what we were talking about before. Kurt asks, but haven't the laws of gravity been verified in the most distant observable galaxies? Doesn't that say that the laws of Newtonian physics are the same at large distances?
Okay, so that also is a great question. And when I say testing the laws of gravity or testing fundamental physics, there's actually two regimes. So one is as a function of time, which is what you're getting at. And we have tests. It's very hard to measure gravity so well at those distant objects, object by object. We actually do. We do strong lensing measurements and things line up. But we also measure the fine structure constant, which tells you, what's the speed of light, what's the, electron charge. And that looks like it's the same at all. Both gravity on those scales and the fine structure constant look to be the same over all of time. Okay, so that's one thing. When I'm talking about the tests we do, I'm not talking about as a function of time. I'm talking about as a function of scale. So gravity works really well on galaxies. It describes everything we see in galaxies. But maybe when I go to scales much, much, much larger, like 100 million light years or 50 million light years, much bigger than a galaxy, maybe in that regime, gravity doesn't work anymore. And that doesn't necessarily have to change with time, but it might just not describe things on very, very large scales. Just like when I go to really small scales, it doesn't work. I can't describe things in quantum mechanics with gravity. so I can't draw what we call as a Feynman diagram with a graviton. That doesn't, no one knows how to do that. So that's a really good question. And what we're testing is, as I go really big, rather than as I go back in time, as I go really big, does gravity still work? And so far it holds up. We're not measuring things at super high precision. It's hard to measure things on 100 megaparsec scales.
So another question, if you go back to 2 slides ago, right there, there's one kind of related to that. What are in the closest voids? Are they completely empty?
Yeah, okay, so great question also. Voids are the areas that are dark in this image, and a void is where there's just less matter. It doesn't necessarily mean it's zero matter. It's very hard to get down to absolute zero protons and zero dark matter. So there's always tends to be something. And even there, you get galaxies forming. So a void really is not an empty region of space so much as it is just a less rich region of space. So there's great inequity in the way matter is distributed in the universe. And those voids are the regions where there's much less matter, but you still get galaxies forming. And there's actually a lot of science we do with voids that I won't talk about today either, but there's a ton of information in this image, and we try to extract as much as possible. And I'm going to talk about the very key things and what results those key measurements led to. But there's a lot more, like studying voids. Okay, so the project I worked on in the last 10 years, for the first 5 years, it was called BOSS. There was no E. That stands for Baryon Oscillation Spectroscopic Survey, which is basically the tool we use to make these measurements of triangulation. In the last 5 years, we put an E in the front, and BOSS turned into EBOSS. And the E stands for extended. So it was an extension to the BOSS survey. And the whole idea was to provide, between BOSS and EBOSS, we make a 3-dimensional map from our location here at the tip of the wedge here, all the way out to the end of the red and blue dots. After BOSS was complete, in 2014, we did not have coverage of this region here. So that whole region of the universe was left unexplored. From something like 7 billion to 10 billion years ago, there was no data. So EBOSS targeted that region. This is the cosmology part of the Sloan Digital Sky Survey. Sloan is probably, Sloan and the Hubble Space Telescope probably are the 2 highest impact facilities to have ever been launched in astronomy for very different reasons. Again, it's quality versus quantity, and Hubble Space Telescope is all about quality, and Sloan is all about quantity. And they both have massive benefits. Okay, so it's in New Mexico. This is a picture of the telescope. It's if anyone has seen anything in Sloan, this should look familiar. And here's a nice plug plate on the right, which is basically a map of the sky with holes drilled at location of galaxies. And then we can observe each of those, about 1,000 objects at a time.
I've got a quick question about that little little slide thing there. I can't remember what you just call it. How accurately are the fibers placed into the holes, and like how accurately are they needed to be mapped onto there?
Yeah, so a galaxy, for example, for like a quasar, it's basically a point source, so it's just whatever the seeing is. So it's something like an arc second, 1.5 arc seconds in diameter. So if you're off by 1/4 of an arc second, you start losing light. I forget what our tolerance was in BOSS and EBOSS. It was probably something like 1/4 of an arc second. And our next project is 1/10 of an arc second. So if we are off by more than 1/10 of an arc second, we start losing information and slowing down the whole program to the point that we can't complete the program. And there's a whole ton of effort into doing the mapping, into doing the drilling, that the drilling isn't, you don't even drill straight down. You have to drill it at angles depending where you are on the plate. It's a lot of thought goes into it. And the plate doesn't sit flat in the focal plane of the telescope. You have to warp it. Anyway, there's a lot. We could spend like an hour talking about all that. It's actually really cool.
Yeah.
So here's the telescope. It's in New Mexico. That's what I said on the last slide. And here's how the plugging happens. Okay. So here's a plate zoomed in. You can see there's 1,000 holes. And this is just like a two-dimensional image of the sky. Every hole, there's a galaxy or a quasar. To get that information into our instrument, we have to run it through fiber optic. Okay. And on this project, we had to have a human being plug the fiber optics into the hole like this.
How do they keep track of which one goes where?
It's also a brilliant technique. So that's what it looks like. It actually takes about half an hour. I'll answer your question, Paul. It takes about half an hour for two people to do that for one plate. And we observed over my two projects about 4,000 plates, each with 1,000 fibers. So that adds up to be about 4 million fibers that had to be manually put into place. And Paul asked the question of, you put these 4 million fibers into 4 million holes, how do you know where they are? And we had a system where you sent light down the fibers, one fiber at a time, and then imaged it with a camera, with a video camera. And the camera mapped out where in the focal plane the light was to help us map that focal plane position to the fiber number. So the person doesn't plan it out. The person just plugs them in. It can be random. And then we decouple it later with this video camera and laser.
So I think in the new James Webb Space Telescope, they do something similar to this, but they use kind of a automated shifting of little pixel holes or something like that. This is basically an analog version of what they're trying to do on there? Is that right?
Yeah. So whenever you want to make observations of many objects at a time, you have to have some way for the light of each object to go into your spectrograph. And you have to have it centered on that object. So what we do is we put a fiber in the location of the object. What James Webb does is they don't have fibers. They have a flat surface that's covered, that has millions of windows in it. I forget how many. They call them micro shutters. And wherever the source is, instead of having a fiber plug in there, they open up the windows at that location and let the light through. So that's something that's called slit spectroscopy. So they basically make a slit on the fly by just opening up these micro shutters wherever there's a source they're trying to observe.
So we have another question. This is from one of our friends in Australia. He asks, if you're aware of what this is, can starbugs be used in place of the plate hole fiber system? Are you aware of what starbugs are?
I do know what starbugs are. Who asked that question?
He's a person from Macquarie University in Australia.
Huh. Okay, so there's lots of different techniques that are being deployed to put fibers into place. In this experiment, we had a human being put them in. Starbugs is an alternate approach. There's also things with magnets that slide the fibers down. There's also ideas of robots where you have there's lots of different ways you can build a robot. There's some robots where you have a fiber pointed straight up and you just tilt it around like this to orient with the light, and the fibers just fill out the grid of the whole focal plane. And there's another thing in my next project, we use these robots with two arms, and with almost like your arm, right? You have a joint at your shoulder and at your elbow, and you can go reach any location within a certain radius of your body with that type of design. And we have motors designed like that So we have, in my next project, we have 5,000 robots, each designed to place an individual fiber in a certain patrol radius. So lots of different techniques. In general, we're trying to move away from what we did here with a human being putting every fiber in a place. And our community as a whole is trying to use new automated techniques like starbugs or like robotic positioners or something else that automatically moves the fibers and doesn't require a person to do it.
So is that
lots of techniques?
Is that supposed to be faster or just easier at knowing where locations of each of the things are, or kind of both?
All of the above. It's also a lot less expensive because you don't have to drill a plate for every single field. There's no custom machine shop. You know, we had to drill 4,000 plates that each cost over $1,000. That's that was something, I think we spent $5 million on aluminum. And then you had to have all the optics and everything else in your telescopes. That's actually very expensive to do this. And you had to pay people to plug. You know, we had 2 or 3 people full time doing this. It adds up over 10 years. But also it takes a lot of time to move one cartridge out, another one in. It takes something like 15 to 20 minutes. And if you had automated robots, you know, in our next project, we think we can do it in 1 minute. So all these reasons.
So for future people interested in fiber plugging, there's probably not much of a job market for you.
I hope this goes the way of, I'm not going to make an analogy. It's very, some old job. So anyway.
Just one more, it's more of a comment, but Adam, the person who asked that about Starbucks, says, thanks for the answer. I don't have a piece of Starbucks, but I'm curious if they are useful as I have seen them being developed. Love the plate hole fiber system. Plates look awesome. The 2DF robotic system looks great in action. Yeah,
so 2DF was a system that was kind of done at the same time as our manual plugging, and that was more automated. That is a pretty cool system. I won't go into detail there, but people should look that up. It's the Anglo-Australian telescope. It's a pretty cool project. And Starbugs is also at that telescope in Australia. I've lost track of whether or not Starbugs has started taking data. I forget if that new technique is being used to take data. There's a new project that's using it, and I think they may have started. I think it's called Taipan, and I forget where it is right now in its operations. Okay, so anyway, there's a lot of things going on. There's lots of cool ideas, but at the end of the day, we all have the same goal: get the light into a spectrograph, disperse it, and see how much flux we get, which is shown on the y-axis here as a function of wavelength, which is shown on the x-axis. So from a spectrum like this, we can deduce what type of galaxy or quasar is emitting the light, and we can deduce the redshift of that light. So what I have here are 4 different galaxies from 4 different spectra. They're mostly like old passive galaxies, and you can see there's distinctive features. There's these 2 lines next to each other that are an absorption. And you can see as I go from my top panel to my bottom panel, those 2 lines keep getting shifted further and further right. Those are absorption lines associated with calcium. And what you're seeing is those lines are being redshifted as I go further and further out in time, or further out in distance, okay? And that's the thing we can directly observe. If we can identify those 2 features are calcium H and K, we can then deduce the galaxy and its redshift and get that 3rd dimension of how far away it is. We don't measure its distance, we measure its redshift, and that's our measure of its distance away from us. It's how much has the universe expanded since that light has reached us. And it's a lot of work. We process 4 million of these, and we have to model them, we have to understand the noise, and we have to understand spurious signal. It's a ton of work to get this done to high precision, but we think we can get it like 95 to 98% of the time, we can figure out exactly what the object is and get it correct.
So just to kind of relate what you're doing here with those calcium lines, people in the amateur astronomy regime often use like hydrogen, alpha, and sulfur and other things to image some objects in space. And so this is just something similar to that. You're just looking at a gas or a element in space that is giving off those lines in similar ways, but at different frequencies, basically, and wavelengths.
Exactly, different wavelengths. This is absorbed. Calcium, it causes absorption. It never causes emission. The Balmer lines, like hydrogen, can cause either absorption or emission depending on the state of the gas. There's also sometimes oxygen lines, but yeah, same idea. The most common line we work with is calcium H and K, because it really is it's the dominant feature in these old galaxies.
And it's easy to pick out from a big line of wiggles, right?
Yeah, it's actually pretty easy to pick out. When the data looks good like this, it gets harder and harder as the data gets fainter, which is what we have working in that regime. I'm showing you pretty nice spectra, actually. But this is the game, and we have 4 million of these to model and measure. And we have to, of course, we have to be very smart about understanding when we're getting it right and when we're not. So a lot of work, 20 years of work went into modeling these. So at the end of the day, we have those plug plates, we run them through the telescope, and we get a map that looks like this. This is our 3-dimensional map. These are real images taken from the images from Sloan Digital Sky Survey, broken up and placed into 3 dimensions based on our spectroscopic data. And you can see there's areas with less galaxies, but even in the voids, there are galaxies. And you can see regions where there are more galaxies. And you can also even see the vein-like structure, the filamentary structure, and you can see places where there's literally galaxy clusters, okay? Right now, I don't see a very obvious galaxy cluster. There is one right there. Right in the middle of the image is a huge galaxy cluster. And this is zooming through the 3-dimensional map. And again, like I said, this is all real data. And this is something like this particular realization was something like 1.5 million galaxies. And it looks pretty awesome. We take this information and we try to collapse it into fundamental statistical properties. So we don't look at one galaxy, we characterize statistically how these things are clustered together. And then we use that data, that statistic to model our cosmology. Okay.
So what we're looking at right there was images of galaxies with an idea of their distance and placement, and then 3-dimensionalized to be able to get this, right? So it's the combination of the actual images themselves and the spectra of those all in one, right?
That's right. So we pull out the redshift from the spectra. So each of those objects had a spectrum taken of it. And then we modeled it, and we got a redshift, and that redshift told us where to put it in 3 dimensions. And then we put it in 3 dimensions. And that's actually what we do. We don't make nice images of the galaxies and make it look pretty like that. We treat them like points, but we then compute all the statistics of the points, how all the points interact with the other or correlate with the other points. And that's fundamental. That carries a lot of fundamental physics in it.
So there is another question. I think you probably will get to this. I don't know for sure, though. But Tom asks you, or says, you can't see a galaxy that is located behind a star in our galaxy, or our galaxy itself. Is there anything else that you can't see through, like nebula or other things?
Yeah, so unfortunately, it's not as easy as it looks to just go out and make this map because of exactly what you're saying. If there's really, there's really bright stars in our galaxy that saturate and just cause all kinds of garbage in the images, and you can't tell what's going on behind it. There's also dust. So in our galaxy, typically as you get closer to the galactic plane, there's more and more dust, and that makes it harder to see through. It's just like looking through fog. And the more dust there is, the harder it is to see faint objects behind the dust. And unfortunately, one thing we're trying to measure is like how all the galaxies are clustered and correlate with each other, but we're punching these ugly holes in our survey with these stars and dust clouds and all this awful garbage. And sometimes the imaging data is not as good. And that introduces spurious signal that we have to spend a lot of time understanding and measuring, so we can make sure we can extract what's spurious and fake signal, or not astrophysical signal, I should say, and what's astrophysical. So a huge amount of our work is separating out the garbage from the good stuff.
So, leading to like these spurious things and things, stuff like that, are there problems with like localized, like transient lights and stuff that go across that are problematic? So you're not likely just doing like one exposure of each of these galaxies, and not taking like one set of data. You're probably doing several, right?
So in Sloan, the Sloan imaging, which was our primary imaging source, we took one pixel basically per coordinate on the sky when we did the imaging. So that's terrible because there's lots of things that show up. There's cosmic rays that hit the detector, and they have to be pulled out. There's also satellites that travel across your field of view and cause long streaks. And that also introduces spurious signal. So we have that, all the stuff we got to pull out and make sure we are not confusing for high redshift galaxies. So all that goes into our map, like all the satellites and the cosmic rays and all of it we take into effect. Also, where's the edge of an image when we take an image? Where are the detector gaps? All this stuff goes in.
You're actually imaging with something that is like multiple CCDs kind of stacked next to each other, right?
Yep. Like our next project, we had a focal plane with 62 CCDs in it. But a CCD, if you put one CCD against another, it's not, there's a gap in what's available for imaging. So there's dead space. And if I then image the sky, I get like a checkerboard pattern of these gaps. And I can see literally 62 nice, beautiful squares with no information in between them. But then we have to dither and cover in those gaps. But on a sphere, it's impossible to cover everything, especially considering that sometimes detectors go dead and there's just a lot of garbage. But we model it all.
So that leads to this question by Tom. It seems like it would be impossible to get an accurate 3D map with all the spurious signals, and to create the 3D map you have to triangulate, right? How far apart are the telescopes, and how many telescopes are there?
So we only use one telescope. And when I say triangulation, the triangulation doesn't happen by placing two different telescopes apart. It's by placing one telescope and looking at two things that are separated in space on the sky. So the triangulation is the telescope is like one point of the triangle, and the other 2 points are out in the cosmos. And that's kind of what I'm showing here on this figure. Basically, if I look at the left-hand side, that's an image of the cosmic background. And if I look at I'm not going to go into detail here, but if I look at the statistics, I can see where do I see signal as a function of scale. Like if things are like, what am I seeing at 1 degree scale? What am I seeing at half a degree scale, on 0.2 degree scales? And you see a preferential bump at 1 degree because there's physics at 1 degree scales because of what happens in the first 300,000 years of the universe. And that 1 degree scale is what's giving me something that's at the CMB, a 1 degree triangle. That's the side of a triangle is separated by 1 degree. Okay. Now that gets frozen into time and sits there in the distribution of matter from the time of the CMB up until today. And the size, that 1 degree size, that's about about 500 million light years across. Okay, so there's an interesting scale in the universe that's about 500 million light years across that gives me an ability to do triangulation. And all around the universe, this is there, 500 million light years across. So that's hidden in the right-hand side, this galaxy. This is a map of galaxies from our real data. And I can pull out the statistics and I see the same wiggles in that distribution of galaxies I see on the left-hand side. And those wiggles are being driven by that 500 million light year feature that's in the cosmos. Okay, so you're literally measuring like the same physics in the CMB today. And you have that same scale out there and you can measure it all different times in cosmic history. You can use it as a standard ruler and measure how the universe is expanding over all of time.
So does the reason why you can look in any direction and see that same scale, is that due to like a property of the expansion of the universe?
It's due to what happened. I tried not to get in. It's due to what happened the first 350,000 years after the Big Bang. It's not the expansion. It's something that got locked into place because of the way photons and electrons interacted with each other. But for this talk, I just want to kind of just say it's out there. There is a preferred scale out there that's about 500 million light years, and that's what we measure. And you can see here on the bottom right, those wiggles are that scale. I'm going to show it in a different way in a second. But these are 3 different redshifts. So this is like 300,000 galaxies at low redshift in the red, at medium redshift in the black, and at higher redshift in the blue. And it's the same feature. Okay, and you're seeing the same pattern at all different redshifts. So I think this is like redshift 0.2, 0.4, and 0.6, something like that, these 3 bins. And you can measure, and that's what we measure. And it's the same physics that's left over from the cosmic microwave background. And that what's nice, Paul, is what you're asking. It's not the expansion. It's the physics is frozen into the CMB, basically. And then we see that for all of time. So it's kind of like that same pattern of dots, is there for all of time. It's a kind of a really oversimplified way of looking at it. And then we can measure that pattern. We know how far they're separated in the CMB. And then we can see how far they're separated today, and we make our triangles, and we get distance measurements. We come out with our surveying stick. Okay, so here is another representation of our data. You can see the radius here in this white is the look back time in billions of years. The very light kind of red, blue, splotchy stuff on the background, that's the cosmic microwave background. That's real data. And here are our different objects we use to map out the universe. And we kind of do it one shell at a time. So you can see in the green, that's kind of one shell of bright galaxies that are fairly nearby. Then you go a little further out in the pink, and you see another type of galaxy. And then you go a little further out in the red, it's another type of galaxy. And then the blue, those are emission line galaxies. The yellow are quasars, and the white are something called the lamina alpha forest. So we literally slice up the universe like an onion, and we measure that preferred feature in each layer of the onion. And then we can get a history of the universe. And these are another way of looking at that preferred feature. And if you look, it's actually, it's the unit. It basically translates, there's a bump there, that preferred bump. That's 500 million light years in radius. So that's something that we statistically are pulling out of these data at each of these slices of the onion. Okay, here is the same information on the left. You can see our precision is represented by those error bars, and you can see we make all these different measurements at different times. So redshift is on the x-axis, and we make 1, 2, 3, 4, 5, 6, 7, actually 8 measurements over something like 11 billion years of cosmic time. And actually, this is better, as I'll show shortly, than anything that's ever been done by any other experiment or using any other technique. And I'll show that in a second. Better precision and better redshift range. On the right-hand side is another thing that's stored in these data. That's that gravitational collapse that we can actually measure over the same intervals of time. And that tells us how quickly matter's falling in as the universe expands. And that's another cool test we can do, which I won't talk too much about. Okay, so here, that's the data. Now let's get into what it means for understanding cosmology. And again, like I said, I'm trying to make this a little bit more technical because I'm assuming that a lot of amateur astronomers and people that read a lot of good astronomy journals, whether Sky and Telescope, they just did a piece on us, or even, who else? New Scientist did a piece on us a few weeks ago. So I'm assuming some background. Here on the top are the results from our measurements of that distance scale, what we call the Barometric oscillation feature. So the CMB can tell us about how much dark energy there is. That's what's on the y-axis, and how much matter there is. That's on the x-axis, but not very well. You can see the CMB is this gray thing. That's a really skinny measurement, but it can't tell the difference between dark energy and matter. That's because it's only one single snapshot. Our data is shown in the blue, and we do a great job of separating out what's matter and what's dark energy. The red is all the supernova that have ever been observed. The supernova are a similar technique to what we're doing. You can measure distance as a function of time. That technique is what gave the 2011 Nobel Prize. So really clear. I mean, this plot here on the left is what led to the Nobel Prize in 2011. The data were nowhere near this good. And now we've surpassed not only that original measurement that led to the Nobel Prize, but we've surpassed all measurements that have been done with supernova. So we're really now, from this single experiment that's run for 10 years on one telescope, we're the premier, we're the premier cosmology data sample for measuring dark energy. Another way of looking at it is on the right-hand side. So we can not only look at what the universe is made out of, but we can look at its geometry. Is it a flat geometry where, if I draw a triangle, the three sides have to be 180 degrees, or is it something bizarre, like drawing a triangle on the surface of the Earth or on the saddle of a horse's saddle? Zero curvature, that's what's on the y-axis. If the universe is flat, it would be zero. And you can see that the CMB here in the gray really cannot tell what the geometry of the universe is. It actually prefers a universe that's very negative geometry, which is a very closed universe. Our measurements here, when combined with the CMB, are shown in the blue. And adding our data improve the best data from the Planck telescope, the Planck satellite, by a factor of 10. So it's really, we really are and that's because we get a wide redshift range, but we are, again, really the premier experiment for being able to test what is the geometry of space. So what is dark energy? What is the geometry of space? Okay, that's using this distance measure. On the bottom panel, this is not as good at precision. You can see it's much noisier measurements, but we can also make these measurements using a completely different sample, a completely different measurement from our data, and that's the growth measurement that I talked about before. But it still leads to the same conclusion that it looks like the universe, at least to the ability of our data, is flat, and it has a dark energy that's described what we call a cosmological constant, which is consistent with Einstein's GR. So it all lines up with Einstein's GR. Okay, now this is a very technical plot, but this is the thing I'm most proud of from our experiment. So on the bottom table, you have 7 different columns for the cosmological parameters that we include in our models. The first 3 are intrinsic, they're basic parameters. They have to be in our model. So our simplest model has those three. Then we say, let's test these different models. Let's see what happens if we change the nature of dark energy, or if we change the curvature, or if we allow the neutrino mass to change. What happens? And as if you look, no matter what we do, each of these different combinations, each of these different rows, the different different test allowing a different type of physics, basically. So one thing you see is the first three rows: dark energy, H naught, sigma 8. Those are intrinsic measurements of our universe. Those things don't change. They still remain at 1% precision, even when we changed all the laws, allow new type of physics into our model. They don't change. So it means that the new physics is really not needed. You also see when we add the new physics, they're described by this curvature, this W, this WA. Really precise measurements and really good. So this is the thing I'm most proud of. We're even able to constrain the neutrino mass better than, by about a factor of 10 better than what's ever been done in a large neutrino experiment. And we're in the regime now of being able to tell you what type of, something about the physics of neutrinos. We're getting very close to, our neutrino mass constraints are so good that I think in the next 10 years, we'll be able to tell you something about the fundamental properties of neutrinos. So again, new types of physics. And that's real. That the neutrinos have to have mass, but we just don't know what the mass is. Okay, then the figure shows how much in this parameter space, how much we've advanced our understanding of cosmology. So in blue is what we knew in 2010, before we started this experiment. And in orange is how much the uncertainty, the central value and the uncertainty decreased by adding our measurements. And if you look at all 7 of these combined, we improved the precision by about a factor of 40 relative to what was known 10 years ago. So if you think about Moore's law, the computing doubles about every 2 years in capability. In 10 years, we're kind of following Moore's law in cosmology, just from our experiment. If you look at the other experiments, going from blue to green is the advances from all other experiments that were not ours. It's not actually quite as good, but I don't include all the parameters that are good for Planck. So it includes like the Planck satellite from space. And then going from blue to red, that's what happens when you take the new supernova measurements, our measurements, some other measurements called weak lensing, and the new CMB. And going from blue to red is overall, when you look at all the different parameters, it's a factor of 1,000 improvement over what we knew 10 years ago. So it's amazing. That's much better than Moore's law. So we're doing quite well in advancing the cosmology, and the precision now is just really, really good. So all of this argues for the simplest cosmological model, where you have a dark energy that's described by something from Einstein's general relativity and very little else. Okay, that's called the Landau-CDM model. However, we can do some other tests. And rather than taking a model and constraining the parameters, we can take a measurement from redshift from early times and from today and see if they line up and see if it's consistent. So we can do consistency checks with these data. And there, things start to break. And this is a complete surprise. What we're doing here in this figure, H naught is on the y-axis, okay? That is the current expansion rate of the universe. And that is something, right? That is, whatever it is, it is. The universe today is expanding at some rate. So if I go at 1 megaparsec, I have some velocity that's around 70 kilometers per second. I go at 2 megaparsec, it's going to be double that, 140, whatever. It's some number. And to measure that, you can measure things locally. You can get a distance measure, see how fast they're moving away from you, measure it further and further and further out. That's like the local distance ladder. That's typically done using techniques like Cepheid variables or supernova, or Cepheid variables calibrate the supernova, and you go further and further out. And that gives you a high value. That's what's shown in the purple here. So that's around 74 kilometers per second per megaparsec. And that's highlighted in this horizontal band. So that's all the local distance ladder measurements. And there's no reason to think they're wrong. They do a great job. They understand their dust. They understand their Cepheid variables. They understand that. They do a great measurement. If they're wrong, it's nothing about fundamental physics. It's something wrong about like the way they understood dust in a nearby galaxy or some weird type of supernova. It's not fundamental physics. It's more understanding their sample. Okay. Our measurements, we do the same thing. To measure the Hubble constant, you need to know velocity and you need to know absolute distance. So our absolute distance comes from a model from the first 300,000 years after the Big Bang. The parameter there is called RD. That's what's on the x-axis in the left-hand figure. And that gives us the absolute calibration of that 500 million light year feature. But if we're wrong, if it's not really 500 million light years, if it was really 450 million light years, that would give us a different value of H naught. From our value, you see here in the dark purple, the pink and the gray. Every way we do it, no matter what we assume about the cosmology, we always get something around 68, which is very, very different from what the local distance measurements are. So they're different. Our measurement relies on a model for very fundamental physics from the first 300,000 years after the Big Bang. And if we're wrong, it's not our data. We show it over and over again that this comes out to be 68. We can do this measurement 4 times over and we get the same answer. So if we're wrong, it means our model is wrong. And it means that something is happening in the early universe that we don't know about. And it's causing us to misinterpret the length of this ruler. What is that? It could be a new type of field, a new type of particle, a new type of neutrino. We don't know. It's right now, this is becoming statistically meaningful that these are giving different results. I think in the next 5 years, we'll know for sure if these really are discrepant. And if they're discrepant, and if we really trust the local distance measurements, it probably means there's a new type of physics that no one knew about beforehand. And that would be a phenomenal discovery.
So would that be something on the lines of how some people talk about how the speed of the universe changed between the kind of like the very beginning and now? Is that what this is looking at?
Yeah, so at the end of the day, it kind of comes down to what was the speed of the universe for the first 300,000 years. That's what tells us how big this feature is. And how fast is the universe expanding for those 300,000 years. And our models, there isn't much going on back then, unless we missed something. Like maybe there was a type of neutrino that would cause a different expansion rate than what we believe to be the case. So, but there has to be a new type of material or a new type of physics or a coupling of dark matter to photons or something else going on that we don't know about. Some new physics would have to explain this, if the local distance ladder measurements are correct.
So is there anything that shows that there is so we have the local one and the one that goes 300,000 years back, or 300,000 years after the Big Bang? Is there anything in the center that can, like, is there a bridge or anything that can bridge those gaps?
Not really. Kind of, yes. There's something called strong lensing time delays, which are kind of in the middle, and they give you the same result as the distance ladder. So a high value of H naught. But the reality is we can measure the expansion history over 11 billion years with our data. So there's not something funny going on in there. That actually is, I mean, this is there's many papers written on this figure right here. But the fact that we can go back to 11 billion years into the past and measure the expansion rate to almost to 2% precision really shows you that nothing is breaking down in that model. So it's really hard to believe that anything it's very, very hard to believe that something has happened in the last 13 billion years that would cause this to happen, that would cause this discrepancy. It really, if it's fundamental physics, the most likely culprits are in what sets this RD thing. How much did the universe expand before the CMB was released, basically. That's the fundamental thing that would have to, that I believe would have to change.
Right.
We're not quite there yet in concluding that that's the case. But if you look at this, I mean, the purple and the dark blue, I mean, they're not even close to each other, which is pretty, it's becoming pretty convincing. And I don't believe that the people who've done the distance ladder measurements have done anything wrong. There's only one catch, is that there's one group who's done a distance measurement using a different technique, and they get something like 70. So there's like 5 groups who get 74 and one group who gets 70. So if that one group who gets 70 is correct, then all this is out the window and there's no discrepancy. So we have to keep, it's really up to these the measurements more nearby now to try to hammer out what the local measurements are telling us. And LIGO actually might be, in the next 10 years, one of the best ways to get at this.
Right, because they measure it through another independent kind of source.
Completely different technique that's not subject to dust, for example.
Right.
They measure the gravity waves. Gravity waves.
I've seen some things that show that the gravitational waves that are coming from stuff are very consistent relative to what they should be, given what we know, given what people have been able to model about what it should happen. And so it's like, if there was something else that could be blocking it, like dust or anything, like some other kind of thing like that, then it would have showed up. But it seems to kind of match what was expected.
So far, every black hole in spiral that's been observed has followed the predictions of general relativity to the precision that's possible. So it's becoming, that would be a great technique. But the problem there is you really need an optical counterpart. So it can't be black hole. It needs to be black hole neutron. It needs to be neutron star.
Right, and they only have like one of those right now.
There's only one.
Yeah. So not very good statistics.
Not measured. It's not competitive with these results yet. You need like 10 of them to get competitive with this. And we have one.
Right.
Okay, so anyway, what's my summary? We measure 11 billion. We measure expansion and growth over 11 billion years. It's really unparalleled in any other technique. All of this that I talked about, I mean, we put out 23 papers on July 20th. There was about 540 pages in total. It's a massive, dense amount of information that I can't cover all here. We had a press release. It was covered all over the world. If I Google search my name and map of the universe, you get like 200 hits from different news outlets.
You're so popular, Kyle.
For a moment, your popularity lasts about 2 weeks, maybe a week, and then people forget. And then if you want to see a little bit more about what we did in the press release, the College of Science webpage and also the physics department webpage has information on this. So you can see our work there. But in the end of the day, what do we have? We're able to measure like the fundamental properties of our cosmological model at like the 1% precision level, which is phenomenal. We've advanced faster than Moore's law in the last 10 years in doing that, especially at least when you consider our work with the cosmic background. The results so far favor the simplest standard model, like no extensions for non-flat geometry or funny behavior of dark energy. And the only surprise is that our measurements fail consistency checks. when we compare predictions from the early universe to the local universe. And that could be very, very interesting and indicate maybe some new physics. And that would be a huge discovery at the level of the discovery of dark energy, if that were the case. But many people were important for that measurement. Supernova, CMB, Big Bang nucleosynthesis, our measurements, Cepheid, supernova, red giant branch. I don't, if there's you can't really give credit to any one group for seeing the potential new physics, or if it comes out to be new physics. It was a community-wide effort. So anyway, that's my summary. Paul had some canned questions, or maybe we take questions from the audience.
Well, we have several questions from the audience that we can go over if you're willing. So let's see. So the first one would be, this is in regard to the James Webb. How will the James Webb Telescope help resolve questions about the large-scale properties of early universe in z equals 10 to z equals 13.5 range?
Okay, so James Webb, I keep making this bad joke about quality versus quantity. James Webb is, again, about quality and not quantity. So James Webb can never do anything remotely like what we're doing. It has a very small field of view. It can observe only a few galaxies at a time. What James Webb can help us understand is when the first stars turned on and when the first galaxies formed.
Right.
So that's a big open question in cosmology. When did the universe become, the way it is now? We say ionized, but basically, when did stars turn on?
So that would give you like a constraint for your data to look back and say that if we see something beyond this, then something else is going on. If this kind of matches there, then something like that.
James Webb, it would literally be just finding the galaxies at early points in time. Just finding one galaxy at a redshift of 8 or one galaxy at a redshift of 9. That's the goal. It's not to do a huge statistical study.
Right.
Can you just find whether or not they even exist at that point in time? So that would be the idea, is to try to measure the highest redshift at which galaxies have formed. That's what one of the primary goals of James Webb. There's other goals, of course, but what relating to the question that was just asked, it's about just identifying a few galaxies at as far back in time as possible.
Okay, so next question. What is the current best explanation, if you know this, for what we used to call the Great Virgo Attractor?
The Great Virgo Attractor. So that that other result that Paul referenced a little while ago is kind of what gets at this. So I don't really like calling things superclusters or whatnot, but basically you can just measure how much matter there is on 1 megaparsec scales or 5 megaparsec scales or 10 or 20 or 50. And nearby, you can measure it at pretty high detail. You can actually get pretty detailed measurements of where there's matter. And what you're measuring is not where their matter is, but you're measuring the velocities of everything that's coupled to that matter or falling in. So you're measuring what we call bulk flows. Bulk flows are the velocities that galaxies have picked up over billions and billions of years as they slowly fall in to these big attractors. And the attractor can be, like I said, 10 megaparsec wide, huge, much bigger than a galaxy cluster. But any overdense region is going to be an attractor, and you can measure these bulk flows, and then from all the velocities of all the different objects, like all these mosquitoes flying around in the flurry, you can kind of figure out where the poor soul is who's getting bitten, right? By how the mosquitoes are flocking into one particular location in space. And that's basically what, even if the mosquito cloud is so thick, you can tell where the person is by how the mosquitoes are clumping together and falling into that area. So that's kind of the idea. If you want to call it the Virgo attractor or whatnot, it's basically just measuring what we call the peculiar velocities or the bulk flows of galaxies flowing into their well.
So it'd just be like the center point for the common gravitational attraction for the entire portion or something.
Yeah, but the reason I don't like yes, that's correct. But the reason I don't like calling it like a single attractor, it's not like a point.
Yeah.
It's an amorphous distribution of matter. I mean, it can be shaped like a sphere. It can be shaped like a river, a long stream. You're gonna have it doesn't have it, these over densities. It can be clumps and the over density here, here, and here. There's a lot. It's very blobular. Especially over very large scales. So a great attractor that's interacting over tens of megaparsec scales is not going to be some clean spherical object. It's going to be more of a collection of objects of varying scales. And that's kind of a fundamental thing in cosmology, is that this structure happens at all scales. So anyway, that's more what really happens. So it's not like a single point. It's more like a blob, a lot of blobs that are kind of congregating together.
Gotcha.
An archipelago of points, maybe. I don't know.
Cool. Next one. What experiments are currently running that search for dark energy and dark matter, deep underground tanks? What experiments should we keep an eye on out for in the media?
Yeah, okay, so at this point, dark matter and dark energy really have kind of split, and they're being pursued with different experimental techniques. So the most promising techniques for measuring dark matter are things in like the bottom of mines, where they're trying to detect the individual particles. All the evidence for dark matter comes from cosmology, and it's really convincing. But the problem with cosmology is we can give you a global property of it. We can say 25% of the universe today, the energy density is coming from dark matter. But we can't tell you what it is at the particle level. So a lot of these experiments are trying to measure the particle level. So the ones that to name, there's three big ones that are happening right now. There's something called LZ. That's using liquid xenon. Xenon starts with an X, but they still call it LZ. So liquid xenon is a great way of tracking interactions of dark matter. And those are and that's a project that's being deep into mine. There's another one called CDMS, cryogenic dark matter search. That's using big blocks of germanium, hoping that a dark matter particle smashes into the germanium and they detect the vibrations in the lattice. And there's another one called it's run out of University of Washington, and it's looking for axions, which is a very, very light type of dark matter particle, if it exists, an idea of a light version.
Yeah, I know what you're talking about. I can't remember the name.
It's called, I'm going to remember it in half an hour. But it's looking for axions, and it's run out of University of Washington. And it's looking for a very particular interaction with a magnetic field. So those are dark matter experiments. There's a lot of ones that may happen in the future. We'll see. Dark energy experiments. The biggest one was in the last 10 years, really was ours, BOSS and eBOSS. There's one called the Dark Energy Survey, which uses a technique called weak lensing, which is hopefully has great potential in the future, although it's not yet competitive with other techniques. And then supernova, which there's lots of experiments out there using supernova, but Dark Energy Survey is one of them. So that's kind of a contemporary of BOSS and eBOSS, is the Dark Energy Survey. And then in the next few years, the next 10 years, there's three big experiments being built in the United States by the Department of Energy. One is called DESI, DESI, the Dark Energy Spectroscopic Instrument. I am a member of that project, and you'll probably be hearing from me about that project in 4 years when we start getting our first results out. That's using the same technique as I talked about today, but with a project that's 10 times larger. So it's to do everything at higher precision. There's another one called LSST, which is now called the Large Legacy Survey of Space and Time from the Vera Rubin Observatory in Chile. That is gotten lots of coverage. It's been an idea that's been in circulation since the 1990s. And they'll start taking data probably in 3 years. And then there's another one, and that's using weak lensing and supernova as well. That's kind of like DES, Dark Energy Survey. And then there's a third one called CMB Stage 4, which is a very exciting name. It will change. But that's a CMB experiment that will be launched probably towards the end of the 2020s. And a lot of the people I used to work with are running that. My old graduate research group is running that. So those are the 3 big ones.
Cool. Okay, let's have the next one. In your recent 3D map release, what are the major bright matter structures in the observable universe, let's say out to z=3? For example, the Boss Wall, Hercules Corona Borealis Great Wall, or the Sloan Great Wall.
Okay, hold on. I'm going to turn on my light real quick.
Okay.
So the Boss Great Wall came out of our project. That's kind of an idea, a lot like this Virgo super attractor. It's basically a conglomerate of clusters that are kind of in a line. Those type of structures form by chance. As I mentioned, over densities can happen on 1 megaparsec scales all the way out to 100 or 200 or 300 megaparsec scales. They can exist over very large scales, and that's an overdensity that exists over a large scale. If you look at the panel on the right-hand side, this is the statistical breakdown of each of these different samples of galaxies and quasars. I'm interested in this global statistic. I'm not terribly interested in individual superclusters. It's very hard to extract meaningful physics from individual objects or individual conglomerates because everything can happen at some probability, and sample sizes at 1 just don't tell you very much. So I like taking all the millions of galaxies and condensing them into statistics that I can then use to constrain something more fundamental. So that's the way I typically prefer to look at these data.
Yeah, I think something like the Sloan Wall was a little bit before there were big surveys about a lot of data, so it looked like there was like this wall of galaxies that nobody really understood until there was more stuff that came along.
Yeah, the Sloan Wall is a conglomerate of clusters.
Yeah.
And that came out of the first large survey. That came out of the Sloan Digital Sky Survey. And then the Boss Great Wall is just a little further out. It may or may not be. I think it's bigger. I don't actually. It's one of the people who pushed that result out came from Utah. He was a postdoc here. I think he was here like 10 years ago. I think he was here from like 2010 to 2013, something like that. But yeah, I just prefer the statistical breakdown.
That's fine. So let's keep going. What are the major bright matter structures above z=3 found in your survey?
Yeah. Okay. So everything above in our survey, everything above redshift 1.1 is a quasar. And I tried not to go into this detail, but now you're asking. Okay, so here's the map from BOSS. This is before eBOSS. And when you're talking about redshift 3, you're talking about, so redshift 2 to 3.5 is this line of red and blue dots, this kind of like these little skewers. So each of those skewers is a map of neutral hydrogen that's been mapped out by background quasars. So that structure, that's real structure. You can even see clustering in it. You can see the red spots kind of cluster together. Red spots, the blue spots hang out with the red blue spots. So we actually break that clustering down into our statistical measurement. And that's what is shown in this white measurement on the very top of this curve. So it's quasars illuminating the foreground neutral hydrogen. And we can see the hydrogen mapping out matter and then make these measurements.
Great. Here's one for kind of the classes and stuff. What is the academic course sequence at the U of U that would get into a course that uses programming the SDSS data stream as a project? What would be the first course in which SDSS data stream programming is used?
Yeah, so, okay, the way the classes at the U are run for the astronomy sequence, for undergraduates, there might be a little bit of data in the introductory class, but it'd be very, very much just a brief intro. It won't be any depth to it. But there's more out of a textbook learning for the first few undergraduate courses. There's some on galaxies. There's a class on cosmology where you'll learn all the math and the physics behind what I just presented. And there's classes on stars. The first class where you start sifting through data and really trying to make measurements is called 6410, Astro and Physics 6410. And that's intended for graduate students, but there's typically a couple undergraduate students in that class as well. And the idea of that class is to learn programming and how to use different tools in Python to look at large data sets in astronomy.
Anil actually did come up with a kind of assignment, a project assignment for 4060 that he did. It's not used every semester though, but it uses some of the Sloan data as part of the project.
I usually think, there's 4060 is the observational astronomy class. And I usually think of that class as analyzing images that you take directly from the telescopes on South Physics. But yeah, you can use databases of other programs such as the Sloan Digital Sky Survey to do science, or to do projects in that class as well. And maybe this semester, I don't know how this class is going to run.
It's been rough planning for it, so I've been helping Tabitha plan for it. So, but yeah, that was one that Anil came up with for the class 2 semesters ago. Because towards the end of the semester, it gets too cold to do anything outside anymore. So we usually go through like survey data and stuff like that to continue the class.
That makes perfect sense, and it's a great topic for that course.
Another question: what is the typical integration time for a SDSS image?
So for the images, where it's just the pictures of the galaxies without spectra, is actually 55 seconds.
Why is it 55 seconds?
55 seconds.
Is that something that deals with the cameras and stuff itself?
That's how long it takes to read out a CCD.
Uh-huh.
And it was done in continuous readout mode. It's called drift scan.
Ah, gotcha.
Where you track the telescope such that the galaxy, the light from each object follows the CCD as the information is being read out.
Yeah, in
55 seconds to do the readout.
In amateur astronomy, they call that drizzle, I think.
Okay.
They have some modes for doing that, but it's not very common.
It's not that common in astronomy either. or in our astronomy either, but that's how Sloan Digital Sky Survey works, and that's how it still took years to map out the whole sky. Our spectroscopy, we spend something like an hour and a half per field, and we can observe 1,000 objects at a time. So each object is observed for about an hour and a half.
Okay, that's quite a bit of time on a single thing. Is that like a single exposure, or is that like multiple exposures over the entire time?
We accumulate in 15-minute increments.
Okay,
So we can do cosmic ray rejection.
gotcha. Another question: what is the level of accuracy and precision for your 3D distance values?
What is the accuracy and precision for
Your 3D, 3-dimensional distance values.
Okay, so our real measurements for each object, the third dimension, is the redshift. And that precision is typically, it's typically something for a galaxy, it's about 30 kilometers per second. That's typically the accuracy that we can measure or the precision that we can measure any one galaxy. A quasar, it's more like, not because of the data quality, but because we don't understand the physics that well. A quasar is more like 400, 500 kilometers per second.
Gotcha. Okay, there was one. Oh, right. Why does the signal stop at 12 billion years? Were galaxies not formed before that time?
Let's see if I can see my map. Yeah, so why does it stop? Why can't we observe past 12 billion years? So yes, there are galaxies past that time and quasars, but we are stuck with the fact that as things get further away, they just get fainter. And it's harder and harder and harder to find objects that are bright enough to observe with our telescope. So it's just, the objects are out there, but they're just not bright enough for us to see a lot of them. So that's the fundamental limitation. That sets our upper limit. We don't do these statistical measurements above redshift 3.5. We don't take any quasars from a higher redshift than that. And that's because there's not enough that are bright enough to actually do the measurement.
Right, so then your statistics would not be meaningful at that point, is basically what it is?
That's right.
So what's like the magnitude of like the faintest galaxies that you can actually detect?
So our quasars go down to, I think, 22.5 in G-band. And our galaxies, our mission line galaxies, were pretty faint. They are fainter. I think they went to 23rd magnitude in G-band.
Wow, that's pretty faint, man.
We're observing it with a 2.5 meter telescope.
Yeah. So I have one question, and that's basically going to be, what is the future path of maybe not just this telescope, but this kind of survey as a whole?
Yeah. Okay. So I should have put a slide on that. That's the critical question. So Sloan 4, which is what just ended, had 3 surveys in it. It had cosmology, which I talked about, but it also had my battery is running low, so we may have to end this soon. They had 3 surveys: cosmology, one of stars, and one of nearby galaxies. And we're basically going to split off in the next year. So my next project is cosmology. It's going to be 10 times bigger. We're going with these new robotic positioners to a telescope in Arizona that's bigger. It's 4 meters. And we'll be running a new project called DESI. So we're going a separate way. The Sloan Digital Sky Survey is not going to do cosmology anymore. They're going to start another program for 5 years studying, they're going to increase the number of stars by a huge factor. They're going to take shorter exposures and get many, many, many more stars than have been observed previously. They're going to get the northern hemisphere and the southern hemisphere, and they're going to go for 5 years doing it. So there are also going to be some other things like time domain spectroscopy, and also some X-ray follow-up and quasar science, but it's not going to be cosmology. So the cosmology and the Sloan communities are going 2 different ways. But both have a very healthy future.
So if I were an incoming student coming into the university as my first year, what would be a likely path for me to get into doing these kind of things?
Yeah, so you would have, for a graduate student, you would have you have both options, because Utah is involved with both the Future Cosmology Survey called DESI. I'm on that project, very heavily involved with that project. And Gail Sazowski is the spokesperson for Sloan 5, and her interests are more in galaxy evolution. So if someone wants to work in large surveys, they have both options. They also have options with our other astronomy colleagues.
So that would mean they would seek either of you out and be like, "Hey, can I take part in this kind of stuff? What would I have to do?"
That's if you want to do cosmology with a large survey, you would talk to me. And if you want to do more theory, cosmology with more theory, you would talk to Zhang, who's another professor in our department.
Okay, cool.
I'm more close to the data, and Zhang is more close to the theory.
Okay, so we have one last question, and then we'll end it since your battery is low, and it's also almost 2 hours. So, what are the X and Y axes on your baryonic acoustic oscillation graph slide?
So this one or this one?
I guess both.
Why don't I do both?
Yeah.
Okay, so here is the baryon acoustic oscillation peak in each of our samples. You can see a big bump. The x-axis is distance. Okay, it's megaparsec times a unit times h to the -1. So basically multiply the value by 1.5 to get megaparsec. Okay, the y-axis is a probability. So it's the probability above random that if I have a galaxy, I have another galaxy at that separation. Okay, so what you see here is if I have a galaxy here, I am actually more likely to find a galaxy separated by 150 megaparsec than I am by 120 megaparsec. There's an excess probability of finding something at that scale. And that is what gives us our ruler. And we measure that probabilistically. So it's the probability of finding something at that separation. That's what this figure is. On this slide, it's now each of those measurements from each of our individual samples. Like when I said we slice up the universe like an onion, and we measure at one layer at a time. Each of these is the measurement of that feature at a different layer of the onion. And so the actual unit on the x-axis is redshift, and the y-axis is the location of the feature compared to what you would expect in a universe that was driven entirely by dark energy that's a cosmological constant. And you can see it basically always lines up with 1, which is why our data indicate that's the universe we live in. My battery is critically low. It's been 2 hours. I hope you all appreciated it, but I should run. Okay, thanks everyone.